work? Okay. Thanks. So this is work with Karthik Sritaran, who couldn't make it, unfortunately. This paper was out a year and a half ago, so some of you have seen the talk maybe. Let me jump into the results. This is very informal. We're going to show a certain equivalence of pathwise online learning regret inequalities that hold for all sequences. So whenever I say pathwise or regret inequality, it holds for all sequences. And certain probabilistic tail bounds for martingales, and in expectation bounds for martingales. So I think the idea that somehow the individual sequence results are related to probabilistic results has been around colloquially, I think, in the community, and this is trying to formalize it. We will kind of say that union bound is like exponential weights, right? So exponential weights is square root of log the number of experts is like expected maximum of n Gaussian. So there's a certain equivalence, and this is trying to get at the kind of a bit more at the heart of this. Okay, so if the second and third are equivalence of second and third might be believable, it's kind of weird that it would be equivalent to a statement that holds for all sequences. So let's present two examples that will illustrate, very simple examples that will illustrate this point. The first one is just bit prediction. So there is a sequence y1 through yn of bits, and we make sequential predictions. So t is a function of the previous bits, and then we count the expected with respect to the randomization of the algorithm, right? So the sequence is deterministic, but our algorithm might be randomized. We count expected average number of mistakes that we made over the n iterations, right? And so if you choose an algorithm A that induces a function which is the number of mistakes, and that's has a value on every sequence. And so no matter what the algorithm you pick, it will be better on some sequences and worse on some other sequences. But it's easy to verify that in expectation with respect to the uniform distribution on the hypercube, it has to be 1/2. There is no free lunch, right? So there is a symmetry between pluses and minuses, and so you cannot hope to do better than 1/2 on average over the hypercube. But the question is, as you run through the space of algorithms, do you get all functions mu sub a? So that's an interesting question. Can you get any function as your mistake bound as you run through the algorithms? And that was the question that was asked by Tom Cover in 1965. So let's say that you can get phi, that's achievable, if there exists a randomized strategy that will get the number of mistakes on each sequence equal to that function phi. So the question is, which functions are achievable? Well, let's look at the functions which are 1/n Lipschitz with respect to the Hamming distance. The result of Cover, which you can prove in 20 minutes, is that phi is achievable if and only if the expected value of phi with respect to uniform distribution on the hypercube, so these are from now on Rademacher random variables independent, equal to 1/2. Okay, so it's a backward induction proof. You can do it in 20 minutes. But it's kind of amazing that so first of all, it says that all functions of this form are achievable. So for any function you set, there is an algorithm, and you can actually get the algorithm. But it's also conceptually interesting that existence of a function which is a regret bound that holds for all sequences is equivalent to just checking whether the expected value is 1/2, right? So that's a statement that is completely void of any dynamics. And this is that's the simplest example of the equivalence. So let's go into the second example of this equivalence, which is a little bit more involved. This is online linear optimization. Let's say we have a ball in d dimensions. D is not important at the moment. Z1 through Zn are arbitrary values in this unit Euclidean ball, and define recursively y hat t plus 1 to be the gradient descent, right? The gradient descent with a fixed step size and the projection onto the ball. This is the online learning procedure. If you start with 0 as the initial point, then you can prove a deterministic regret inequality. This is completely deterministic. It holds for any sequence of z's, and for any comparator y star, you have this upper bound of square root of n, right? So that's a 1/square root of n rate, or 1/square root of t if you use t instead of n. So this is the deterministic inequality. And let me just rewrite this as in the following form. These are equivalent. We're just choosing y star to be optimal in the direction of the sum. So it's a unit vector in the direction of the sum, and this is the deterministic inequality. It's a completely deterministic statement. Okay, so let me just rewrite this and put 1 here. So that's the first statement. And now what we're going to do is we're going to plug in a martingale difference sequence. And because this holds pathwise for any sequence, we can also compare the tails of the left-hand side to the tails of the right-hand side, and as we plug in this martingale difference sequence. And so what we conclude is that the probability that this norm of the sum has this tail behavior is upper bounded by probability that these inner products have this, has a certain tail behavior. But these are martingale difference sequences with values in -1, 1, because this is a projection onto the ball, this is in the unit ball, product is between -1 and 1, and y hat t is measurable with respect to z1 through zt minus 1, right, by construction. So this is indeed a martingale difference sequence, and so Azuma-Hovding immediately gives us a tail bound. If you look at this is a kind of weird that you know, if you try to prove something like this, you know, imagine this is a spectral norm, you would have to take a union bound at some point, right? You take a union bound, you prove something for one vector, and then you take a union bound. And magically, we seem to have avoided any union bound here. And the punchline is that the union bound is already baked in some sense, in this deterministic inequality, right? So we didn't have to actually do it. Okay, so let's not stop here. Let's integrate the tails. Actually, we don't care about this center part. All we care about is this relationship. Now let's integrate the tail, and of course you get the expected Euclidean norm of the sum of the random vectors is upper bounded by square root of n. Now this you could have proven in one line with Cauchy-Schwarz, of course. But what is interesting is that we've shown in the previous work, starting with the work with Peter Bartlett and Jake Abernethy and Ambuch Tewari, that there exists a strategy such that a regret inequality can be upper bounded, or regret statement can be upper bounded by supremum over martingale difference sequences of the expected norm of the sum, right? By going to the minimax dual. And so what we've got now is that 1 implies 2, 2 implies 3, and 3 implies 1, with a worst constant possibly. And this concludes the loop, right? So in a certain sense, all of these statements are equivalent, right? This is super simple, but I think it's worth stating that these statements are somehow inherently related. So the summary so far is that a inequality that holds for all sequences is equivalent to a tail bound for the norm of the sum, right, of random vectors, martingale difference sequences, which is equivalent to the expected statement. And in particular, there are a couple of curiosities, which is, one of them is that, you know, generally, a result about the expected value doesn't imply the sub-Gaussian tails, but by going through 1, now we can amplify the tails of for that random object, which is interesting. It also gives us a playground to, you know, take an inequality that we know, regret inequality, that your favorite inequality that you know, and try to conclude some interesting high probability statement, which is what we're going to do, and vice versa. Take an inequality about martingales that you know, and try to see what is the deterministic counterpart to that. So I think that's the beginning of kind of an interesting exploration. And whether this is limited to this linear structure of the problem, but we already know that no, because the first example was a bit prediction. There is no linear structure there, right? Okay, so let's try to generalize this result. So what can we expect? So if you have a Hilbert space or, you know, Euclidean space, if you have independent vectors, mean 0, then you would expect such an inequality to hold just by Jensen inequality and opening up the square, canceling the cross terms, right? So a natural question, okay, let's take this as the inequality. Is there a deterministic statement, a regret statement that is equivalent to this, right? That's a natural question. And in fact, if we can show this, hopefully we can show it for any smooth Banach space. So a Banach space is too smooth if there exists a equivalent norm such that the norm squared is a smooth function. And for any such space, you would expect this inequality exactly for the same reason that you would expect it in the Hilbert space. And so indeed, that's the case. We can show that the ability to prove this, which is 5, is equivalent to having a regret inequality with an adaptive regret bound. So you're able to show this if and only if you're able to show this in whatever space you live, right? Whatever Banach space you take, these two statements are equivalent, right? Okay, so this certifies, if we know that this is possible, it certifies that this is possible in that space. But thankfully, we already know what the algorithm is. At least we know it in Euclidean case. I think it was shown in a previous talk. The extension to a general mirror descent is not difficult. So you take Bregman divergence, which is with respect to a function R, which is once strongly convex on a unit ball of the dual space. And now you define the mirror descent update, which is the time-changing step size, the linear part, and the Bregman divergence, right? The usual thing. The important thing is that you take the step size to be data dependent up to little t, up to this current time step, and then you get a regret bound which was certified before purely non-algorithmically. In the Banach space is defined as a linear function, right? There is a linear function in the dual space and in the primal, right? Good question. Yeah. Okay, so how about tails? So this is just the deterministic inequalities versus expected statement. What about the tail bounds? What can we expect? Let's just think about what we can expect. Well, if you think about real valued random variables which mean 0, then you would have, of course, this statement, but you would also have some behavior like the t-statistic, right? If you take the sum and you normalize it by its own sum of the squares, you would expect that this converges under mild assumptions to the normal law, and this was studied in probability theory over the past 20 years, of course, more than 20 years. And non-asymptotically, one can prove that if z's are symmetric, then it has a certain sub-Gaussian behavior. Maybe the constant is a little bit different here. Okay, and the nice thing about such statements is that they're completely self-normalized. There is no n. It's a very natural statement. And in fact, one can prove them under milder assumptions than the central limit theorem behavior. Okay, and indeed, this is just a consequence of mirror descent. Quite amazingly, a ratio inequality of this type, so you have a martingale different sequences in some Banach space, you have a norm of the sum, and now you compare it to square root of the variation, right? This statement is just an immediate consequence of mirror descent, right? And I don't know any other way of proving this, which is simple. So people have tried to prove statements like this for a long time, and it's kind of interesting that it's just a consequence of mirror descent. Okay? So here I stated for conditionally symmetric, but the statement for general martingale different sequences is a little bit, just a bit more complicated. There is no boundedness assumptions here on the z's. You just need the second moment to be finite. That's all. Okay, so a very nice statement. So you can compare it to the results of Pinellas 94, which is what is used by many people in kernel learning. In learning theory for concentration of random vectors, and that statement is with respect to a worst case sigma. So this is not a data dependent one, but a worst case upper bound on the pointwise over the probability space. Okay, so the remaining a couple of minutes, let me go into the supervised learning. Does the result of cover extend to something more interesting as well? In the way that the Euclidean case extended to mirror descent, and indeed that's the case. So suppose nature reveals the x's, the learner chooses the y's, let's say these are plus minus ones, and then nature reveals the true outcome. And the goal is to get an adaptive regret bound such as for all sequences, so again, in red, this is a deterministic statement that holds pathwise. A sum of the losses is upper bounded by the comparator plus some adaptive penalty, right? So such a statement can be shown to be, well, you can rewrite it in this form. And now we can show that that statement is equivalent to just checking the expected, a certain expected value is less than 0. So again, this completely deterministic inequality that holds for all sequences is equivalent to simply checking this in-expectation statement. And once again, so this has to hold for all predictable processes, which are trees in the language that we used in the past papers with Karthik and co-authors. And again, by taking this inequality and plugging in a martingale difference sequence, you get a tail-bound, a high probability statements, which you can then integrate and get the expected value back. And so once again, all of these phenomena are equivalent. Okay. All right. So let me conclude in the last minute with a generic high-level point of view. There's an interesting circle where you can put martingale inequalities being in high probability or in expectation. Pathwise regret inequalities, which hold for all sequences, and there is an interesting connection that we just outlined in this talk. There is something that I didn't talk about, which is geometric properties of the space, and this is something that was used implicitly in the proof of the mirror descent result. It's the existence of the strongly convex function. Now, this connection between the uniform convexity of the space and behavior of martingales was studied in probability theory, starting with the work of Pizier and others. The connection between the uniform convexity and pathwise regret inequalities, well, at least in the optimization, closely related optimization context, it was studied by Nemirovsky since the 70s as well. And we just closed the loop with the top arch. But there's much more to this kind of circle, and I want to give a plug to Dylan in 10 minutes. When one wants to prove finer inequalities, such as certain adaptive regret bounds, it's not enough to look at uniform convexity as the geometric property, but something that comes from the study of martingales by Burkholder, which is a non-trivial object that Dylan will describe, and that gives improved and optimal adaptive regret inequalities in this world. So there is much to be gained, I think, by going back and forth in either direction, either getting better probabilistic inequalities starting with deterministic statements or vice versa. And I want to also, in the last 10 seconds, mention that there is something in probability theory called trajectorial approach, and in the last 5 years, it was shown that the Dubs inequalities for martingales and Burkholder-Davis-Gundy inequality, they all have a deterministic counterpart. So we're showing something of that form again, and deterministic inequalities are these regret statements. Thank you.
All right.
Yes.
So do you know Pizier's proof of the equivalence of COLT type and uniform convexity? Are you sure that they aren't using mirror descent in this proof?
They're not using mirror descent. They're using the function implicitly. Yes. Yeah, you can kind of see that it's almost there, right?
I mean, there is no. I guess my question is, there is no other way to prove this than to do a potential-based approach.
That's right. But in the full version of the paper, we look at generalization when there is no linear structure, and you can still talk about type and cotype, but there is no geometry. But you have to go through these pathwise inequalities, and you can certify that there is some algorithm. It's not mirror descent. We don't know what it is, but we can certify it exists, and then you can conclude probabilistic inequalities.
So you mean in a nonlinear setting,
Yeah.
in a metric setting?
No, just general supreme over a function class, and then the martingale, which is indexed by that element of the function class. It's a generalization of the norm, which is a supreme over a linear, over a ball, right?
There is also the metric generalization of those notions.
That's right. Now we're in this stuff. Yeah.
One very short, burning one. Okay, let's thank Sasha again.
Thank you.